Welcome everybody. My name is Dr. Sarah Kaiser, and I am super excited to welcome you to the next installment of the Quantum Software Talk series. Here at the Unitary Fund, we really want to make we're a nonprofit that really helps support the quantum open source ecosystem. And one of the things that we're really excited to be able to do is to help show off all the really cool projects that are already out there that can help you with your research or your investigations into and working on quantum computing and quantum technologies more generally. With that, I'm really excited to have our guest today, Stephen DiAdamo. Let me switch over here. Hi, Stephen. He's a developer on a project called QuNetSim, which is a quantum-enabled network simulator that adds common quantum networking tasks like teleportation, superdense coding, sharing EPR pairs, to help you develop quantum networking protocols. You can kind of test, it seems like you can test it with different sort of network configurations and stuff like that. Because, we all know that classical computers need networking, so, it seems like a natural extension that we're going to need to figure this out for quantum devices as well. I think I'm just going to turn it over to you, Stephen. Certainly chat here if you have any questions during the talk portion. And there's also going to be some exciting demos, which I'm super excited about. Please feel free to put questions in chat at any point, and I will try and interrupt and ask as appropriate. So take it away, Stephen.
Right. All right. Thanks a lot, Sarah, for inviting me for this. Looking forward to getting started with the talk. Okay. So in the beginning of the talk, I'll just be going through some slides to explain what the project is, what QuNetSim does, how it works, and things like this, and kind of like future paths that we want to take with it. And on top of that, we'll show a live demo if all goes accordingly. And then, explain a little bit about what we've built also on top of QuNetSim as an idea of what others can use it for. And you can use it also directly, but there's also alternative applications that can be used with QuNetSim. So to get started, I think it's important to understand what is a quantum network and what does a quantum network mean in the context of QuNetSim. So I tried to keep it a little high level, but in general, a quantum network is a collection of network nodes. And these network nodes are connected over a network so that they can transmit quantum states between themselves. The quantum network also enables these parties in the network to share entanglement with themselves. So, for example, if we just take this picture here, we see Alice and Bob in the network, but they're not directly connected, so there's no wire connecting them one-to-one. Oh, sorry. Okay. Yeah, and so what Alice does here is she puts a qubit into the network, and the quantum network moves this qubit through the network, and then it has to be routed through this network like any traditional classical network, and eventually it arrives with Bob. Another thing that happens is entanglement generation is not so trivial in a quantum network because it's not so easy to move qubits through the network. So there's different ways to ensure that Alice and Bob can also share an entangled pair if they need to. And I'll get a little bit more into that later. So in general, that's a quantum network. Quantum network is kind of like a classical network for qubits in a very high level vision. Okay, so then the question is, what is QuNetSim? The QuNetSim is a Python framework for developing simulations of quantum networks. For both these networks are designed such that they have both classical and quantum connections. So when I say classical connection, I mean these connections are only used to send classical messages. For example, sending the message hello can also be routed through a quantum network because the quantum network is kind of a generalization of a classical network. So QuNetSim integrates both the classical and the quantum part of the network, and it tries to emulate this network of layer of this type of network. And so what does it do exactly is, as I was kind of getting to, it's allowing the users to develop and test protocols for quantum networks. So quantum networks currently is kind of an ongoing field of research where we're not sure what is the best use case for the quantum networks. Even if we have such a network that is perfect in all aspects, then so what? What can we do with it? And this question is kind of an open question, I would say. And what the intention of QuNetSim is to allow people to develop applications for quantum networks. It makes it easier to develop them, makes them easier to debug it, and it makes them easy to test against different network configurations as well. So some examples of what you could potentially try with QuNetSim is doing variations of quantum key distribution. There are network protocols regarding distributing money, the quantum money protocols, anonymous transmission. Anonymous transmission is sending messages to each other in a quantum network where you don't know who sent it, or the other parties don't know that these two parties in the network are communicating. Another thing that we put into QuNetSim is this ability to listen in channels. So this means that if two people are communicating, let's say Alice and Bob like before, then we can integrate some kind of eavesdropper that listens in on the quantum channels. And this is important because in quantum key distribution, you can share secret keys with perfect security. And that means even if there's an eavesdropper listening in the channel, the key that is distributed is perfectly secure. It's a perfect secret, and the eavesdropper can't know what that secret key is. So there could be other protocols that exist that we want to test against security and secrecy, and therefore we integrate this feature into QuNetSim. So QuNetSim also includes a lot of common networking tasks. As I said, the goal of QuNetSim is to develop new applications for quantum networks. So it would be a shame to have to develop all the old ones first in order to make use of them. So we, for example, integrate the most common features of quantum network, and this is to be able to do quantum teleportation, quantum superdense coding, and GHZ state distribution, and others. So these things would potentially take some effort by the user to work on, to develop every time they need them. So we're hoping to make like a toolbox of features so that people who want to develop new applications have something to work with as a foundation. And we also include this ability to do multi-threading. So this is not so obvious, or maybe it is too, but sometimes there's two types of ways to simulate, well, maybe more than two, but there's two common ways to simulate quantum networks, and this is event-driven simulations, and this implies that the timing of the event is random as a random event. So this is simulated time. But QuNetSim uses a different approach. It uses real-time simulation. So this allows the users to perform things like idle behavior of a quantum network. So with a random time simulation, I think it's maybe I'm wrong on this, but I think it's harder to implement something like sit and wait for some number of seconds so that something can happen in this meantime. So this is common in network, sitting and waiting for something to happen. So we hope to find some more applications that can be done with a quantum network during these idle periods. So we have this feature as well, and this is kind of a unique aspect of QuNetSim. So the pieces of QuNetSim is kind of we motivate the pieces of QuNetSim based on classical network architectures. So in a classical network, there are various layers of the network. The common layering structure is called the OSI structure, the OSI model. And so the OSI model is 7 layers deep, but we only consider the first 3. And these first 3 are the application layer, the transport, or the upper 3s, or it depends how you order them. The upper layers are the application layer, the transport layer, and the network layer. And so the first layer is this host layer, or the application layer. So the hosts are these nodes in the network that run applications, and they process and store quantum and classical information. So they transmit quantum information between each other, they store it, they can also manipulate these things and perform quantum operations, unitary gates on these qubits that are in storage. And they act as 2 different types of nodes. So there's an end node and a relaying node. The end nodes are the ones that run the application, and the relaying nodes simply move information onward in the network, do routing. And they can be programmed to run any kind of application that's desired. Next is this transport layer. And the transport layer takes the information that the host wants to transmit and packetizes it. What that means is it adds additional information to the intended transmission so that the network knows what to do with this payload, so to say. So this header, so it adds header information. So for example, it adds the sender, the receiver, the protocol that it needs to run, payload type, etc. Isn't that so important what the header has, but it adds the header information so that the network knows how to move this packet around. Transport layer also is checking to simplify the development of quantum network protocol. Sometimes it's necessary that a protocol needs to have entanglement generated before the protocol can run. For example, in quantum teleportation, the two parties need to share an EPR pair in order to teleport their qubit state. So what the transport layer does here is it verifies that the two parties share entanglement before they run something that needs to use entanglement. That's kind of a unique feature of this quantum network because classical network, of course, there's no entanglement generation. And then we have the network layer. The network layer routes the information in the network. So one thing that's unique about the QuNetSim network layer is that you can program the routing algorithm directly. So in general, what we have is the shortest path algorithm, like Dijkstra's algorithm or something, and that will determine the way a packet moves in the network. But in a quantum network, it could be that there's a more optimal route based on some other properties, and that we leave open to the users. Maybe they want to test something like using the route that has the most entanglement already established, for example. And this is open to the user's interpretation or their creativity to test their own routing algorithms. QuNetSim has a simple noise model, kind of as something in process to figure out the best way to do this, but in the current state, it has kind of a loss model at the moment, and a very basic noise model. So that you can lose packets in the network, or you can find out that the qubits, while they were being transmitted, had some errors applied to them. So it's kind of a basic noise simulation, and it can be switched on to use multi-hop entanglement distribution. So this is kind of back to where I said you have to do some type of protocol to establish distant entanglement, so to say. So what I mean by this is if Alice and Eve here want to share entanglement, they are not able to directly transmit this. Generate entanglement is one step. They need to go through Bob first, and this is called we use an entanglement swapping procedure. This is a feature of a repeater network. I think it's okay if I skip the protocol. I don't think it's so crucial to know what it does. So how does QuNetSim work? Stop. I think I'm okay. Yeah, here we go. So it's basically.
Stephen, a couple people were asking questions here that I just wanted to, before we moved on. M. Stetchley asks, are there classical routing algorithms? Do classical routing algorithms also work here, or is it totally different?
So in QuNetSim, it's kind of two networks at once. So you have the classical network and the quantum network, and there's a two disjointing. So of course, both of them can be programmed to route as desired. So I guess the answer to that question is, if I remember correctly, that there's a separation between the two, and you can program them separately. So yes, classical algorithms do work here.
Okay. And Nathan was also asking, are there similarities between QuNetSim and Simulacron?
Yeah.
I always have trouble saying that one.
Yeah, no problem. Simulacron is quite similar to QuNetSim. Simulacron, I don't want to misrepresent it. I used to use it often as well. And it's a little bit, so it's more focused on the application layer, I would say. And it also is designed, I mean, I think the main thing of simulacron was that it should run on multiple devices. I don't know if that was the key goal, but it's one thing that it does do. And what it does is it allows you to run a quantum network simulation between two computers, let's say, that are connected via local area network. I think this makes it slightly harder to program, but it's also a real-time network simulator. You also design the network topology and things. It's quite similar, but it's missing the kind of the network layer features. I mean, they could be there, just not as accessible. And it's missing the built-in features. For example, if you want to run quantum teleportation, you would have to find a library to integrate into on top of simulacron or implement it yourself. Yeah, so there are similarities and there are differences. I think in general, if we compare lines of code to run the same simulation, I would guess it's fewer lines of code to run in QuNetSim than simulacron.
Sweet, thanks so much.
Yeah. Okay. So yeah, how does it work? It's basically a bunch of threading and thread management. I'm not sure it's maybe not as interesting as the other parts of the talk, but yeah, it's essentially the hosts are running in threads, the network is running in a thread, all of the hosts have a queue, all the packets go into a queue. When the packets arrive in a queue, something in QuNetSim happens. And that's essentially the whole system. It's just moving packets along the queue, queue to queue, triggering events based on the status of the queues. I mean, that's, I guess, a kind of a standard way of doing such things. It's using the Python package it's all done in Python, so it's using Python's multi-threading libraries. Yeah, I think I don't need to go too much into that. So. Yeah, okay. And underneath QuNetSim is the quantum simulation. So QuNetSim actually just does the networking part, but the actual qubit in quantum simulations are done using other backends, what we call backends. And these are, what I mean by backend is they're pre-existing qubit simulators. So what we do is we take libraries that do quantum simulation, and we basically put QuNetSim on top of those things. And this way we have access to really good quantum networks, quantum simulation platforms without having to reinvent our own, even though we have the ability to if we wanted to. So for example, we integrated Project Q and CQC and simulacron. This is interesting to see. We actually put simulacron underneath QuNetSim and run our tasks on top of it. We've also developed one of our own, is EQSN. And the benefit of using EQSN is it's well designed for multi-threaded systems. We recently put in QTIP, and yeah, we have it open-ended, so if someone wants another qubit simulator, it can work as well. So if I were to summarize these ones, I would say QTIP works the fastest and the most reliably. Project Q is also very fast, but we found it works best if you run your protocols only one time. CQC and EQSN work reliably and with multi-threading. We haven't tested it so much with QTIP, but I think it would also work as well. So they all work quite well, but some work better than others. So it's a little bit of playing around.
So I have a question related to that, actually. So you have all of these different backends. How did you go about designing? Obviously, there's probably some API between what like the QuNetSim code and these backend codes, and then or the backend systems. And like, how do you pass information back and forth? Is it like kind of custom, like JSON or something like that, or what does that interface look like?
Yeah, it's basically just a wrapper. So we've made our own qubit object, and then we have what that means is the qubit object calls something like qubit.xgate, okay? And then what that does is it goes into so let me start from the beginning, actually. Let's say we are just creating the qubit. So that goes into so let's say we're using QTIP. So in QuNetSim, we generate a qubit. Then that triggers another event that calls the QTIP's creation of a qubit. And now we store that the qubit object of QTIP in our wrapped qubit. I wish I had a picture for this. Maybe it's tricky to explain for me. But anyway, so then what happens is you call next not a gate, a logical gate on this qubit. And then again, all it does is it wraps it. So it goes from our qubit object, calls the X operation, then goes into the Q-tip operation. The qubit is stored as a Q-tip object, and then calls the X operation in Q-tip terms. So we have to do this kind of one by one. We just implement it as it would be in this own library, and then just wrap the behavior.
Gotcha. So you're kind of doing custom subclasses for each of the different backends.
Yeah.
Cool. Michael asks, are you limited to networks of qubits, two-level systems, or can you have network components with large Hilbert spaces, such as atoms trapped in a cavity?
Yeah, it's just qubits. Well, that's an interesting question, actually. I think, especially now that we've integrated Q-tip, something more with some other types of networks might be something we can add. Because the other three are qubit simulators. Oh, okay, maybe I'm not so familiar, could be wrong, but I'm pretty sure the first three are just qubit simulators. And Q-tip can do more than that quite easily, and that's something we just recently integrated Q-tip, but I think changing this to something like a three-level system simulator could be on the table if we have, yeah. But currently just qubits.
Sweet. Great question, Michael.
Okay. And so the pros and cons of using QuNetSim is that it's very high level and very easy for beginners to use. So as we'll see in the next examples, it takes very few lines of code to get something working. It allows access to the network layer, so one can test routing algorithms. It's easy, well, in my opinion, at least, it's easy to debug. So we have tons of logging messages. The qubits are stamped so that we know where they are at all times in the network and things like that. So it's nice to see, if I'm just writing my own network protocols, it's nice to see step by step what's happening. And that's possible to do in QuNetSim. We can install it with pip, so it's nice to just install with one line of code. And then there's also a script that comes with the pip library that you can template an example. And active development is there. So for example, there's other other network simulators that I didn't go through in this talk, but some of them tend to lose. I think some of them you see in the Git repo, they're not active as much as they used to be. And I think if one wants new features or finds a bug, it's not guaranteed that they get their bug fixed. So at least with QuNetSim, we're still here. We're still working on it. And even today, I've just closed an issue, so that's nice. And the cons of using QuNetSim is that it's quite high level, and it's not. For example, the noise models are not realistic in the sense of if I were to build a quantum network today, would my protocols work on that network? It's not possible to test that in QuNetSim. Large-scale simulation is kind of based on the performance of one's computer. If I want to run something with 20 nodes and multi-party entanglement, these things don't scale very well. So it's only good for kind of smaller scale simulation. It assumes this packet-based quantum internet or quantum network structure, and is not also guaranteed. It's not known for a fact how the next quantum networks, the first quantum networks will work. Will they be routed with packets? Will there be a transport layer? Is not known. There's no standardization. So it's something like, I think one takes a risk by writing their protocol in QuNetSim because there's no standardization. It's not guaranteed that quantum networks will work the way QuNetSim has implemented it. So who I think should use QuNetSim, again, maybe this kind of covers a whole lot of people, but beginners for sure. For example, as an educational tool, we use QuNetSim as in our lecture. We give a lecture on quantum networks, and part of the lecture is to implement some of these protocols in QuNetSim. And based on the feedback of the students, they found it nice to have some hands-on practice with these protocols, helps them to understand what's actually happening, rather than only having one source of pen and paper simulation or something. Kind of just seeing the mathematics, but also being able to implement it and see step by step how does it work. So I think as a beginner or a student, it's nice to learn about quantum networks with QuNetSim. Instructors also, because it's nice to give assignments or homeworks to the students in this framework. For one example that's really nice is one student wrote their master's thesis using QuNetSim, so they integrated a complex feature into QuNetSim and wrote a master's thesis on that. As researchers, as I said, I think QuNetSim is good for prototyping network protocols, even if it's not physically, perfectly realistic. At least you kind of get an idea for what could work if we had an ideal quantum network. So the first development stage, I think researchers could potentially use this platform to test their protocols.
Sorry, I got another question for you.
No.
So how do you handle the exponential growth in Hilbert space with the network size? Do you always simulate the full Hilbert space, or could you use something like matrix product states to exploit the network, which often have low overall entanglement?
Yeah, exactly. So, for example, we don't store the entire quantum system in one matrix. If I just generate 100 EPR pairs, those are just 4x4 matrices. And then we just store 100 4x4 matrices rather than 4, times 2 to the 100 or something. I don't know if my math's correct. But you can see like that scales it, makes the scaling a little bit easier. But optimizations are kind of based on how do our backends handle it. We don't do any quantum simulation in QuNetSim. It's always up to the backend. So yeah, I think maybe the answer is we don't handle it, but at the same time we try to make sure that we're not using backends that store the entire system in one go. Actually, Project Q does, so that's a bit of a contradiction, but in small scenarios it's okay. If you do a lot measurements often enough, then Project Q is fine. But if you build up a lot of entanglement, then measure, I think, this causes chaos. I want to be careful about that a little bit. Yeah. Okay, so I'll go on. So I'll just show it a quick example, and then we'll go to the live demo just to get a rough idea of what it looks like first. So what usually happens when you're writing a QuNetSim simulation is we define protocols for all of the end nodes. So in this case, this will be a two-party protocol with the sender and receiver. And in this case, all we want to do is teleport a qubit. So the sender's protocol is to create a qubit, and the qubit is owned by this particular host. Then they perform an X operation on the qubit, and then they teleport the qubit. And what these parameters mean is, okay, it's the receiver who they want to send it to, the qubit that they want to send, okay, and send, I mean teleport. And then await act false means don't wait for the receiver to acknowledge that the teleportation was successful. And you see in teleportation, I said you need an EPR pair ahead of time to run such a protocol. And in this case, we just ignore it. We let the QuNetSim handle that for us automatically. And on the receiver side, the receiver is expecting the teleportation. That's part of the protocol. And they're expecting the teleportation to come from this sender. And they will wait 10 seconds for it to come. This is kind of a mysterious number. It's not really important. It depends on the computer, how much waiting time is needed sometimes. But I mean, 10 is overkill for sure. So this qubit will arrive in this receiver's storage, and then they'll just fetch it from the storage. And then what they do is they measure it, and that's it. So that's a quite simple example. So that's usually the first step, define the protocols. Next step is, I guess, ordering of the steps is kind of up to the user, but second step in this case is to define the network. So we just take the network instance, then we define our hosts. So in this case, we have Alice, Bob, and Eve. Okay, this should mean say Eve. But
Steven,
yeah, we have 3 nodes in the network. Then we define the connections between them. So Alice is connected to Bob, and and then Bob is connected to both Eve and Alice, and then Eve is connected to Bob. Then we start them. When you call start, they start listening, and then we add them all to the network. And then as a third step, we can now execute protocols. So all we do is we tell Eve to run the sender protocol, which we defined above, with Eve. And then we tell Alice, oh, I think I just mixed up the names. Then we tell Eve to run the protocol with Alice, the receiving side. And then we just wait for the threads to stop, and then the simulation is done. And then what you can see is some logging messages. Okay. And we see Alice starts processing, Bob starts processing, Eve starts processing, Alice teleports to Eve. They don't share an ETR pair, so one has to be generated. So that happens, and then finally Alice can send her qubit via teleportation. Then we see Eve received the qubit and measured it in the state 1. And then everything stops. So let's kind of see step by step what happened in this protocol. So I'll try now a live demo. I hope I'm in time. About half an hour, yeah. I think it should be okay.
Oh yeah, you got time.
And this will be a bit more complex. So I'm going to show how to implement the CHSH game in QuNetSim. So the CHSH game is not so complex, but the way it works is there's 3 players. There's a referee, and there's Alice, and there's Bob. And what happens in the beginning of the game, to start a round of the game, is the referee sends both Alice and Bob a qubit, sorry, not a qubit, a classical bit, either 0 or 1 at random. So he picks 2 bits uniformly random from the 4 possibilities and sends one to Alice and one to Bob. Then Alice and Bob make some kind of decision, and then they send a bit back to the referee. And they win this game if A and B is equal to the XOR between X and Y. I hope, yeah. And the constraint is that during the game, Alice and Bob can't talk to each other. So they can't coordinate during the game, they can coordinate before the game starts. So therefore, Alice doesn't know which bit Bob received and vice versa. Okay, so let's try to program this and see if we can come up with a strategy. Oh, I didn't mean to do that yet. I need to stop sharing screen. Switch. Okay. So you should see my terminal.
Yep, we got it.
Okay. All right. So what I've done so far is I've just installed QuNetSim via pip in a virtual environment. But now what I'll do is I'll do a template. So this is a template script. So I just type template. Then I pick my file name. Let's try chsh demo.nopy. In this game, there are 3 nodes. Okay, now I've got my chsh demo, and I can run it firstly. So the first thing it does is it builds just a very basic example, and it's runnable. So what does it do? All it does is it sends 5 qubits from Alice to Bob. Sometimes, I mean, yeah, maybe if I cut my camera, my computer might run better, but I think we got time. I can.
Yeah, I think it's running okay as long as it's running okay on your end.
Yeah. Ancient computer. Okay. Let me just, I'll kill the camera temporarily. Okay.
The second you killed it, it's like, okay, you've given me some breathing room here.
Yeah, so what happened was we have 3 parties and one was sent, yeah. So all it was a general, I'll show you the code now of what that was. So that's this. So what happened was we have 2 protocols, like I was saying.
Oh, we can't.
And what happened?
It's still sharing your terminal?
Yeah, sorry. Yes.
No worries.
Switch. This one.
Sweet.
Okay. All right, so we had, what happened was protocol 1, protocol 2, and there were 5 qubits generated, had a marked gate was applied to it, then they're all sent one after another, and then the receiver just receiving them and measuring them. Okay, so let's modify this file. to play CHSH game. So
Can you make the
firstly,
font a little bit bigger, please? Thanks.
yeah. Sorry.
Sweet.
Readable now, right?
Oh yeah, thanks.
Okay, so I'll just import the necessary libraries. Okay, so we just need actually these two things. So I'm going to disable the logging so that we don't get flooded with messages. So first what I'll do is I'll implement the classical strategy. So in the CHSH game, the way to win it classically is just to send from both Alice and Bob a 0 state, because that gives them a 75% chance of winning the game. So all we need to do is make Alice and Bob receive a classical message and then return 0. So I will just quickly define this. This is how many times we're going to run the game so that we can determine the statistics. I will modify this number according to how much my computer cooperates. So I'll just modify this to be classical. So what she needs is the host object, and she needs the referee's ID. And all we do is for I in H plays. So we're going to play this game this many times. And what happens is you can ignore the input because we don't care.
It's always a good sign when you're playing a game. I don't care what the input is.
Because it's, yeah, exactly. And it's just because in this case, Alice has the input she receives does nothing to change her response.
Yeah, no, makes sense. But I just don't want to play board games with someone who's just like, I don't care what you tell me, I'm going to do this regardless.
Yeah, I mean, yeah, let me know if I'm going too slow. I have the demo already written up if we just want to read the code too.
No, this is cool. It's always nice to kind of gives people time to process as you're writing the code.
Okay, that's good. So Alice and Bob do the same thing. They both send 0 back. So we just can run like this. Actually, I didn't even need to write it twice, but just for clarity, we show that they have no strategy. They just send 0. So now I would also need to program the referee. So for statistics, we will figure out how many times they win the game. And then we do for plays. So what the referee has to do is he makes a random choice between 0 and 1 for X. I think I might have mixed up the labeling here from X and A. Oh no, I think X and Y was right. So it picks 2 bits at random. And then the referee, let's do it like that, classical to Alice ID. So it sends Alice X and sends Bob Y.
Nathan was just asking, could QuNetSim be an interface for a quantum network with real hardware, or is it like QTIP so that it's not designed to interact via like actuators with real devices?
That's a good question. One of the things we're working on, and hopefully I'm not disclosing anything, but we've separated this simulation of quantum out of QuNetSim completely. So we took this backend out and put it into a Raspberry Pi, and then we use QuNetSim through microcontrollers to control the quantum simulation. So the answer is yes, I guess. Depends. I mean, and obviously that's through a microcontroller. What we hope is we can eventually replace the Raspberry Pi and then do put it into some kind of physical hardware at some point.
Oh, that's so cool. Yeah, Nathan also says open hardware. Cool. Yeah, no, that's by being able to separate that interface there, where like you can just swap out a simulator. The interface should be defined just as well for classical hardware. So, or sorry, for hardware in general.
Exactly, yeah. So that's why we were thinking about this a little bit, because it's kind of a natural thing. Imagine being able to program an experiment in Python. I don't know. I don't know. Maybe they already do it, but I'm not sure.
There are some neat like experimental control Python packages like that I've used in the lab and stuff like that. Things like um, instrument kit and Q codes. But yeah, a lot of that is it's a lot of work to get the individual device drivers for each function generator and everything in the lab to cooperate nicely, because despite there being communication protocol standards, does everybody adhere to those? No.
Okay, almost done with the referee, and then we're almost done. So then I just print the statistics. Let's do. Okay, I hope everything is going to work. Oh, this is double. Okay. I predict that's going to be a problem.
No. I was going to ask, so the inputs to those three functions are IDs? Is that the same, like, where do the IDs get defined, or is that part of kind of the host class, like
Yeah.
other code?
Yes. So well, there's only one requirement, that this parameter is the host that's executing the protocol. So this always has to be a host. But the rest are optional, and we'll show you. So here, for example, we will do on something like, what did I call it? Referee? Yeah. I spelled it wrong, didn't I? And then what we have is we just put in the IDs here. This is where they come in.
Gotcha.
So it's, yeah. Let me just sure I got this all.
You're doing great.
I'm
Live coding is
expert.
live coding is hard, so.
I don't know how long it's gonna take, but I was hoping.
Oh, no.
I think I'll just do the classical one, and then I'll paste the quantum part after.
Sounds good. And certainly chat here if you have any questions for Stephen as we're kind of going through this, either about the demo or kind of about their path in quantum, kind of what they studied, anything about that. Please feel free to put them in chat.
All right, so now what I'm doing is I'm building the network topology. So in this case, I put an add C connection because the only thing that Alice can send to the referee is classical information. This prohibits qubit transmissions.
Gotcha.
And then we do the same for B. And then we do the same for C with a twist. Yeah. Oh, yes. Good. Yeah.
Oh, this is where I'd probably use the find all, replace all sort of thing, and then be really sad later when it didn't work.
exactly. Okay, so now we add all the hosts to the network. Okay, I just cleared all this stuff. So now we've defined all our hosts, we defined the connections amongst the hosts, and now we just, oh, I already had it here. So now we can run the protocols. We want C to be the ref. We do host C. Actually, I'll put this at the bottom for simplicity. C will be the referee, and what they need is the IDs of Alice and Bob. Let me just make sure I have this Alice and Bob. And then we want, I just can't believe. And then I said something like this, blocking equal true. And this is just so that it doesn't stop the network before the referee is done running. And host A and host B will run.
Yeah, they both need their classical strategies, right?
Yes, exactly. Okay, this should be with the referee. Yeah, I could just simply paste A, B, and C here, but okay, and I think that is everything. Let me just verify with my notes. Yeah, okay. So this is the classical strategy. And then what we should see, if all runs accordingly, something around 75%. So I'll just switch back to terminal. Okay, and then I run. Let's see what errors occur.
That's always the cross a finger and like, please let there be good error messages here.
Ah, yes, at least one error. I forgot to import the logging. Done with it.
I wish I had a counter for like how many times like I do live coding on Twitch and like that I'm just missing a semicolon at the end of a line. And I have thankfully chat is very helpful in reminding me that, but
Somehow the place is not getting carried into the. Let me just quickly add them. Okay, hopefully now. If this one fails, I'll just run the prepared one.
no worries, no worries. Can you also tell us about what your favorite kind of development workflow and tools here are? So it looks like you've maybe got Sublime Text or something like that, and Terminal here on a Mac.
Yeah. So I don't generally use. Hold on, let me just. Here it is. I was calling it play instead of play. I generally use PyCharm because I'm just used to it. Sublime I use for just. Oh, sorry. Sublime I just use for really quick things because it's my computer just handles it. It's really lightweight. Sublime, yeah. But generally I'm using PyCharm and I use, here we go. Yay. Okay.
Sweet.
So if we increase this number to something like, I don't know, 100, maybe 200, then we should see getting closer to 75% because this is the optimal classical strategy. So let me open after this one. Yeah, so it should be around 75% because that's the best that these players can do. And now,
Andrea was going to ask real quick, can one use QuNetSim to train a quantum network for a particular task? I wonder if and also I wonder if QuNetSim could have integrations with Taquito for quantum games.
Let's see. So for the neural network or part, I'm complete noob at machine learning. I don't know even what that means. To train a neural network, I don't think so. I don't know if it's using, maybe, I'm not sure. I mean, it does simulate a network and it moves information through a network. Training a network, I don't know. I actually even I don't know.
Yeah, it'd be like if you had setups for non-local games like this, rather than giving it the quantum strategy, trying to have like a feedback loop, with probably some other algorithm to help it find the actual optimal classical strategy as like some sort of optimization routine. That would be interesting.
Yeah, with Taquito though, I wonder if it can be. I mean, one could compare there. For example, I could import Taquito here and then put my parameters into Taquito and see like, does my protocol meet the optimal? But Taquito, I use a little bit. I really like it actually. But if I recall, it's the quantum information package for Python. Yeah, and therefore, yeah, we can compare the theoretical limits to ideal communication channel scenario. Okay, but what I wanted to show with this demo is that surprisingly, if we use a quantum strategy with the same game, then what happens is we get an advantage. We should win this game with higher chance. So I'll show the code quickly. It's not so important what it does, but Alice is running a quantum protocol. She's no longer abandoning the input. So based on the input that the referee sends, something actually happens. Same as Bob. And then I will just show that it runs quick. Oh, yeah. And then we can just do, I think, yeah, run this one. Oh, not run. Python. Yeah, so let's see. So it's running with the quantum game. So what is it doing first? One thing is so I said they can strategize before the game starts. In this case, they can generate entanglement between themselves before the game starts. And now they win with a higher chance than classically. Yeah, so this was the demo.
Quantum mechanics works. Or is at least consistent. Sweet. I always love the CHSH game. It's I think a really good kind of like teaching tool and a good way to kind of just really demonstrably show here's what you can do with entanglement in a pretty easy to define game. Cool. Well, I'm going to double check with chat here. Make sure if you have any other questions about the demo or anything, please feel free to please feel free to put the questions in chat. And I actually had a couple questions for you too. Oh, sorry, you put up some.
Yeah,
there we go. Yeah. Because so. Did you work on this project then with the Quantum Open Source Foundation, like as a mentorship thing, or you have the link there?
Yeah, so there's a couple of slides that I skipped over, but we used in the latest Quantum Open Source Foundation last term to build something on top of QuNetSim. And this is this project interlink, but yeah, I guess I won't explain it now, but one can check this link and see what it does. But the original QuNetSim, we were working on it. Then I found out about Unitary Fund during the process.
Sorry, I'm just putting the link in chat for folks for interlinking. Okay. But yeah, no, what's really cool is so the original QuNetSim project and this new Interlinkin project, which is building on this, were both Unitary funded projects, which I think is just a really cool kind of example of, kind of the impact that those can have in getting some really awesome tools out there for doing useful things. So some of the questions I like to ask maintainers and folks who come on the program, so you've worked now in the quantum computing space for a while. You're in academia. You're building open source tools. What is one skill that you wish you could go back in time and teach yourself, like before you got started doing everything? Like for me, it's like making sure I've fully explained and understood the block sphere, because I was really confused. Like I tried to basically apply that to multiple qubits. It turns out that that's really only good for one qubit, and I just got stuck for a long time trying to understand everything through that. So like, what is it could be an open source skill, like, or it could be a quantum concept. Like, anywhere on that spectrum, what do you wish you could have taught yourself sooner?
I think there's a book that I read during my master's that I really wish I read when I was in my bachelor's or even in high school. And this book is something called like Learning How to Learn or something. I don't know. I don't know if maybe it's cliche or something, but when I got into my master's, I switched countries from Canada to Germany, and I was dealing with a different academic system, different methods of teaching, and I realized I'm like baby fed in Canada somehow compared to Germany. They're spoon fed, sorry, not baby fed. Because the way that they teach here is a bit more intense. It's more independent learning, and this book it basically teaches you, you're not alone in being confused in things. And the way we learn is more like, in school, just keep reading this, read it once, get ready for the test, write your test, forget everything you learned, prepare for the next test. I mean, I guess everyone has this experience, but then I was thinking, like, this book kind of tells you don't treat learning like that, but treat it like anything outside of learning. Like when you learn, for example, to play a musical instrument, you play the scale once until you can play it once, and then you never play scales ever again. It's like never the case. You play scales for your entire musical career. So why do we treat the same, like something like that? I don't know. It's kind of stupid.
Well, it's not stupid at all. Like that's a really important skill. Does it have a red cover, like, and it's like somebody holding a book open on the cover?
I have an old version, I think it could be, but the
Okay.
author is Barbara.
Okay.
Barbara something.
Oakley. Yeah, I wanted to make sure I found the right one and wasn't just putting a random book link in the chat. Yeah, I there was kind of it wasn't exactly about how to learn, but I got a great book from another postdoc, or from a postdoc at my institution while I was writing my thesis, and it was like how to write a good thesis, which I thought that was like a pretty niche book, but in particular, it was really good at showing, like, kind of teaching me how to like design visuals and like clearly and concisely communicate things, like kind of the same skills as like writing academic papers. Like I went to a liberal arts undergrad where like we were taught to write papers, with very flowery language and to beat around the bush a lot. So Aaron says, I gotta go, but thanks for the interesting talk and demo. Have a good one, Aaron. Yeah. Well, so that's definitely a good resource. What are you most looking forward to? You kind of hinted at there's some possibly like hardware, kind of back end stuff. What are you most excited about for the future of QuNetSim, or maybe your studies or career more generally?
Yeah, I guess it kind of combined. Somehow the field is picking up so much steam lately. I think just seeing what's going to come out in 5 years. I mean, this 5 years, it's kind of taking this joke from someone else, but like this 5 year number is always the 5 years. It's always like in 5 years we'll have this, in 5 years we'll have this. And I think that was funny. What's coming in 5 years? Let's find out. Kind of weird. But they were saying 5 years every day for 5 years ago, so we we're kind of in that. Anyway, but basically I'm excited to see what comes out in the near term. We're seeing so much development, so many startups coming up, lots of funding coming out, so many ideas, so many people getting into this stuff. Especially that it's coming from, with this field, it's so many diverse backgrounds, and therefore I think a lot of interesting ideas can come out of this field. I mean, because it's so new and everyone's new to it, so anyone can get into it, and they might have a unique idea, a unique perspective than purely from a physics background or purely from a math background, maybe, yeah.
Yeah, I know the 5 year ahead timeline was the same story I got in 2012 when I started. So I feel like that hasn't panned out. But okay, so one last question I had for you, which was, if somebody is really excited about QuNetSim and they wanted to get involved and start contributing, what suggestions would you have? Are there certain tasks or issues, or like how can they do that?
Mm-hmm. I think the thing that's always been in the back, not always, but for a long time in the back of my head is designing the network topology. You have to do it in code. But I think having a drag and drop like okay, there's too far away from quantum, but having an interface to be able to like build the network with a drag and drop, and then click on the nodes, and then program the nodes in Python, and then press play, and then run the simulation. I think as an educational tool, removing as much code as possible would be really cool. That's something that I would like to see. Other than that, just integrating as many examples of network protocols as possible, just demonstrating how it can be used. So we have had about 10, 15 examples implemented, maybe more than that by now, but there's a whole bunch of them that we haven't had a chance to do ourselves. So those two things, the two avenues, taking an existing protocol that you find in a paper and simulating it, or making it easier to use somehow.
Makes sense. Yeah, I'll have to check to see which QKD protocols are implemented. That was my PhD topic, so that's always near and dear to my heart. Cool. Well, thank you again so much for joining us today. I always really love doing this and getting to kind of show off all the awesome work that you and all your collaborators are doing. Yeah, so I think that's all I got. I'll put some more links again in chat for all the projects and everything that Stephen had on the slide there. But yeah, have a great day, everyone, and go out there and help make the quantum open source ecosystem better.
Thanks a lot.
Cheers, everybody.